In this chapter, we will study basics about transistor. In the transistors, we will study both bipolar junction transistor, that is BJT, and unipolar junction transistor, that is FETs. In FETs, there will be JFET and MOS FETs. We will see later there. Bipolar junction transistor BJT is called bipolar. Bipolar means both types of charge carriers take part in conduction. While in unipolar junction transistor, only one type of charge carrier take part in conduction. Only one type of charge carrier will take part in conduction. Now we will see basics of BJT, bipolar junction transistor. Bipolar junction transistor BJT. In bipolar junction transistor, both type of charge carriers take part in conduction. Next, if both type of charge carriers take part in conduction, then majority and minority both will be there. If majority is take part in conduction, that is good. If minority take part in conduction, the device will be noisy. So BJT is a noisy device as minority carriers as minority charge carriers take part in conduction. The BJT is noisy device. Next, the input impedance of BJT is very low, or I can say that input impedance of BJT is low. Next, it is commonly used as an amplifier. It is commonly used as an amplifier for amplification of the signals. So these are the important points for bipolar junction transistor can be asked in the examinations. Now we will see the construction of bipolar junction transistor BJT. A BJT basically consists of three different layers of semiconductors. One is called emitter, they're called base, and last collector. In a bipolar junction transistor, either emitter and collector can be P region or they can be N region. If emitter and collector are P region, then base will be N region, and if emitter and collector are N region, then base will be P region. So a bipolar transistor will be either PNP or NPN transistor. In bipolar junction transistor, this emitter region and this base region both form a PN junction, this junction, which is represented by Je and called as emitter junction or base emitter junction. And this base region and collector region both forms a junction written as JC, and this junction is called collector junction or collector base junction. Now we will discuss the basic operation of BJT and the grouping and areas of the different layers in the BJT. Now we will consider NPN transistor. In NPN transistor, emitter is N-type material, and basic operation is that this base emitter junction will be forward biased and this collector base junction will be reverse biased. If this base emitter junction is forward biased, majority charge carriers will take part in conduction, and uh, this P region, which is base region, is a lightly doped region. If it is lightly doped region, then majority charge carriers in this region will be very less. And emitter is highly doped region. If base emitter junction is forward biased, then the majority charge carriers from N-type region will be injected in the base region, and when these charge carriers are injected into the base region, this base region there will be a large number of electrons, and this region also an N-type region, but the concentration of electrons in this base region will be very large as compared to concentration of electron in this region. So we can say that between these two regions there is change in concentration with respect to change in distance, means concentration gradient is created. Concentration gradient is created. If concentration gradient is created, these charge carriers will diffuse from higher concentration to lower concentration, means these charge carriers will reach to the collector. This is the basic operation of BJT, and now we will discuss about the doping and areas of the region of three layers. Now, earlier we discussed that basic operation includes the majority charge carriers of emitter region are injected into the base region, and these injected charge carriers will then diffuse towards collector. Now we will discuss about doping of three layers. First, we want to we want to inject the majority charge carriers that are electrons from emitter region to base region. If these charge carriers will be injected into the base region, so emitter region is highly doped in order to inject more number of charge carriers. Now this base region is lightly doped because we are injecting these majority charge carriers into the base region. If base is highly doped, then there will be large number of holes in this base region, and we are expecting these injected charge carriers to reach to the collector. Due to large number of holes in p-type region, there will be large number of recombinations in the base region. So base is lightly doped in order to reduce the recombinations in base region. In order to reduce recombination, we are doping this lightly. And there are some reasons of moderate doping of collector region, but which are not that much important. So we will just say that collector region is moderately doped. Moderately doped. Collector region is moderately doped. If these are the doping of three regions, so we can say that doping of emitter is greater than doping of collector, and doping of collector is greater than doping of base. This is the range of doping for these three regions in the transistor. Now we will discuss about the areas of three regions. There is no particular region for moderate area of emitter region, but yes, there is region for less area, less width of base region. If we are injecting majority charge carriers into the base region, then we should ensure that the concentration of electrons in base region, that is n, and concentration of electron in collector region, as collector is n type region, this will be very large, but as we are injecting electrons into base region, the electron concentration in base region will increase and should be greater than n dash. This we have to ensure. If n is greater than n dash, so we can see that if we move from base to collector with a distance x, there will be change in electron concentration. So concentration gradient will be created. If concentration gradient is created, then only these charge carriers will diffuse to the collector. Now the area of collector region is kept very large. This is kept very large to ensure that the heat generated at this collector junction should be properly dissipated to the surrounding. As this PN junction, when operated, this junction or collector junction is always reverse biased, and for a reverse bias junction, its resistance is very high, and also the number of charge carriers that are crossing the collector junction is very large. Means at this junction, collector current IC is also high. If this current is high and this resistance high, then at this junction the heat generating IC square into R will be very large, and this much heat should be properly dissipated to the surrounding, otherwise the BJT will burn or uh, will be destroyed. So This collector region is kept very large so that the large area of BJT should be in contact of surrounding. We cannot increase the area of a base because if a base area is increased, then high concentration gradient will not be created. Now we'll see symbols of BJT. This is the symbol for NPN transistor. This is collector terminal, base terminal, and this is emitter terminal. For this transistor, this collector terminal will be N-type region, this base will be P-type region, this emitter will be N-type region. For this transistor, the actual direction of emitter current IE will be in this, and collector current will flow in this direction, while base current will flow in this direction. If we consider this BJT as a junction, then total outgoing current should be equal to total incoming current. According to KCL equation, total outgoing current, that is IE, should be equal to total incoming current, that is IB plus IC. Now this is the symbol. This is the symbol for a PNP transistor. In PNP transistor, collector will be P-type region, base will be N-type region, and emitter will be a P-type region. In this PNP transistor, the emitter current IE will flow in this direction, while collector current IC and IP will flow in the outward direction. Again, if we consider this transistor as a junction, then total incoming current IE should be total outgoing current IC plus IP. Also, we will define terminal voltages for a NPN transistor. This is collector, base, and emitter. Between this base and emitter terminals, the voltage drop will be denoted by VBE, base to emitter voltage, while the voltage drop between this collector and base terminal will be denoted by VCB, and the voltage drop across these terminals will be denoted by VCE. These are the terminal voltages of BJT. Now we will see the operating regions of transistor BJT. BJT is operated in 4 different operating regions depending on the biasing of emitter junction and collector junction. First operating region is active region. When operated in active region, base emitter junction or emitter junction is forward biased, while collector junction is reverse biased. When BJT is operated in active region, it can be used as an amplifier. So when we want to use a transistor BJT as an amplifier, we will have to use it in active region. Next, saturation region. Now in BJT, if base emitter junction is forward biased and collector base junction is also forward biased, then In this particular biasing, a transistor is said to be operated in saturation region, and when it is used in saturation region, it behaves like an on switch when it is used in switching circuits or switching applications. Number 3, cutoff region. When both the junctions are reverse biased, a BJT is said to be operated in cutoff region, and in cutoff region it behaves like an off switch when it is used in switching circuits. So when biased in active region, BJT can be used as an amplifier, and biased in saturation and cutoff, BJT can be used as a switch. When operated in saturation, it will be on switch, and when operated in cutoff, it will be off switch. Number 4 is reverse active region. Reverse active region. When collector junction is base emitter junction is reverse biased and collector junction is forward biased. If we bias BJT in this particular fashion, when base emitter junction is reverse biased and collector base junction is forward biased, it we can see that it is just like active region, and we have just reversed the biasing of collector junction and emitter junction. And when we reverse the biasing of collector and emitter junction, BJT operates in active region, reverse active region, and when it is used in reverse active region, it cannot be used as an amplifier, means its gain is low. So if we try to operate emitter in place of collector, means if we interchange these two layers of BJT, then BJT cannot be used as an amplifier. It will not provide any gain to the input signal.